Hello and welcome to MiniLecture 7 on discrete functions, sequences, and recursion equations. Alright, so we've talked a lot about functions before, and a lot of times we've talked about continuous versions of these functions. For example, we might have the continuous sigmoidal function or S-shaped curve here, where the domain of this curve is all real numbers or a subset of the real numbers. In contrast, a discrete function is a function that has a domain that doesn't include all points. So a very common version of this is where the domain is the integers or the positive integers. So for example, this discrete version of the sigmoidal curves has the domain of the integers. So we can only plot points. Now confirm with yourself that this function over here is continuous and this function is discrete. Remember what the meaning of the continuous is, that you don't have to pick up your pen in order to draw that curve. And then over here, we're going to use a discrete function where we have to pick up our pen in order to draw it. So we plot point by point by point. Now test yourself and confirm that these functions are indeed functions by using the vertical line test. So pause the video here and then come back and let's look at whether or not these are actually indeed functions by using the vertical line test. So we can use the vertical line test here, and it only ever intersects that curve at a single point. That is also true of a discrete function. It's just that sometimes we draw a line and it doesn't intersect any of those points. All right. So a sequence is a type of discrete function whose domain is the natural numbers. Now recall that the natural numbers are the positive integers, that they're strictly positive. In other words, we don't have zero. So a sequence can be a list of numbers like A1, A2, A3, all the way up to AN that have an ordering that's given by this index 1, 2, 3, up to N. All right, so some examples of a sequence are the discrete function an is equal to n over n plus 1. So let's evaluate this. All right, what happens if we plug in 1? N equals 1. We get 1 over 1 plus 1, and this is equal to a half. Then we could have a 2, which is 2 over 1 plus 2, which is 2/3. Let's plug in 4. We get 4 over 1 plus 4, which is 4/5. This is a sequence. If we plug in 3, we get 1 plus 3 is equal to 3/4. And that is our sequence. All right, so notice that the n here is our independent variable, and our a to the n is our dependent variable. So that is the mapping between what we typically think of as a discrete function and a sequence. All right, now let's think about this other sequence, example 2, where we have bn is equal to -1 to the n minus 1. All right, this is a little bit more complicated, so let's work this out. We have, if n is equal to 1, then we have -1 all raised to the 1 minus 1. What is -1 raised to the 1 minus 1? Well, anything raised to the 0th is simply 1. If we have 2, then we have -1 raised to the 2 minus 1, which is equal to -1 to the 1, which is just -1. -1 to the 3 minus 1 comes out as -1 squared. If you square a negative number, it becomes positive, so this is just 1. And finally, you could evaluate this last one, and you would see that it was -1. So let's plot these two examples. Let's plot b of n. We have to plug in the value at n equals 1, and b of n, if we draw that in red, we end up with a value of 1 at 1, a value of -1 at 2, a value of 1 at 3, -1 at 4, and you could keep going and have 1 at 5, and you see that this bounces back and forth, back and forth, back and forth. All right, let's see instead the function an. All right, an, if we plug in 1, we get 1/2. All right, 1/2 is 0.5. We get this value right here. If we plug in 2, we get 2/3. That's 0.66666. So it's going to be equal to somewhere around there. If we plug in 3, we get 3/4, which is 0.75, which is this point right here. If we plug in 4, we get 4/5, which is this point right there. And then this point right here. So we're getting closer and closer and closer to 1, but we never quite get there. All right, so those are our two sequences here. Okay, so a sequence can be termed either convergent or divergent. So we saw here that this number gets closer and closer and closer to something, but never quite gets there. That is known as convergent. So if you approach a horizontal asymptote, such as an is equals 0.8 to the n, if I plot those points here and I kind of draw a continuous function through that, they're going to get closer and closer and closer to this horizontal asymptote here, and that is known as a convergent sequence. Not all sequences are convergent. You can also have divergent sequences, so the number can fly away, or it can be like this case here, where it neither goes closer to something or further away. It just goes back and forth, back and forth, back and forth. So both of those are known as divergent. All right. Similarly, we can characterize sequences as oscillatory or non-oscillatory. So we saw an example of both of these in our first little bit, where b of the n was oscillatory. It oscillated back and forth, back and forth, back and forth. And we also saw a case where we had a non-oscillatory sequence where a to the n smoothly approached something without bouncing back and forth. So if we take a to the n is equal to minus 1.2 to the n, notice that usually if you do a minus sign to the n, that this is oscillatory. So this is going to oscillate back and forth. So in our first example, we had minus 1 to the n minus 1. So if we raise a negative number to a power, we get something that's oscillatory. If we oscillate back and forth at 1.2, it gets further and further and further away from each other. So this is oscillatory and divergent. We could also have a non-oscillatory function, so we have a positive number to the n, and it's still divergent, so we still have 1.2 and 1.2, so it still diverges, but it no longer oscillates. Similarly, if we have a value in here that is less than 1 and we take the power of something that's less than 1 to the n, it's negative, so it's going to oscillate, but it's going to converge towards something. So here it's converging toward a horizontal asymptote of 0, and here we're converging in a non-oscillatory fashion because we don't have a negative sign, and we're converging toward a horizontal asymptote of 0. All right, so notice that oscillatory sequences tend to have a factor of minus 1 to the n in them, and then if you're raising something to the power that is greater than 1, it is going to diverge. If you're raising something to the power of less than 1, it's going to converge toward a horizontal asymptote. All right. So in the equations that I've given you above, those sequences had simple formulas where you have some function of n, where that independent variable is written as a subscript to denote that it's an integer. And then you wrote that as a simple function like minus 0.8 to the n. But not all sequences have simple expressions like that. And instead, we often have to write them as a recursion equation. A recursion equation tells you what the next value is given the current value. So a recursion equation gives you the sequence where it gives you the next step, an plus 1, given some value of the current step, a of n. In order to specify a sequence with a recursion equation, we need two quantities. We need the recursion equation itself that tells us how to iterate the sequence, and we need the initial condition, which is where to start. So here we have our recursion equation. And here we have our initial condition. So this says, if you're at 0, start with 2. So we're going to put a 2 right there. And then to evaluate the next step, we say, what happens next at the first point, given I know what happened at the 0th point. So, for example, if we want to know what happened at a equals 1, that means that t is equal to 0. So that is a 0 plus 6 over 2. Okay, you can do this. That's 2 plus 6 over 2, which is equal to 8 over 2, which is equal to 4. Okay, now that we have a1, we can evaluate the next step, which is a2. So note that a2 is equal to, okay, so if I have this is equal to 2, that means that t is equal to 1, so we have a1 plus 6 over 2. So the next step in terms of the previous step, a2 is equal to a1 plus 6 over 2. That's 4 plus 6 over 2. That's 10 over 2, which is 5. All right, let's do one more. That's a3. How do we do a3? Well, if we plug in 3 is equal to t plus 1, that means that t is equal to 2. So the previous step is a2 plus 6 over 2. All right, so here we have 5 plus 6 divided by 2, which is 11 divided by 2, which is 5.5. All right, so recursion equations are evaluated in a step-by-step manner. All right, let's do one more example. So we can write a recursion equation as a(n plus 1 as a function of the previous step. That's what we did here. We had a(n plus 1 as a function of a(n). Here, n is represented as t. But we could also specify a recursion equation where we say the current step as a function of the previous step. They're equally valid. So we could rewrite this recursion equation in the next step way by saying b of t plus 1 is equal to b of t over 2. So the future step as a function of the previous step. So b of t plus 1 is a function of b of t over 2. All right, we have our initial condition of 8 here, so I'm going to put my 8 there. Now let's evaluate the next step. So if t is equal to 1, what do I have here? I have b of 1 is equal to b of 1 minus 1, which is b of 0, so 8 divided by 2, which is 4. Okay, what's the next one? Well, we have b of 2 is equal to b of 2 minus 1 divided by 2, which is equal to b1 divided by 2, which your b1 is 4, so we have 4 divided by 2, which is equal to 2. Okay, if we do this again, you're going to get 1, and you see that this is a convergent sequence, and this is going to be a divergent one. 8, 4, 2, 1, 1/2, 1/4, and so forth, and this just keeps getting bigger and bigger and bigger. So b is a recursion equation that corresponds to a convergent sequence, and A is here a divergent sequence. All right, so with that, I'm going to leave you with a self-study question that applies a recursion equation in a biological context, and I'll see you in class.